So last time we talked about how we can create an error resonances. Is the mic okay? Too loud, too small? I hope you can hear me breathing. And the idea was that we want to create kind of strong error resonances to produce a strong response in our system. And this is always a good idea to have a strong response. Now, I looked at it. I don't think there is a very simple way to show how you optimize your resonances. You can see already if we're doing the simple kind of 2-photon resonances, there are a lot of parameters which goes into that. So you will really need to work on your experiment, see what things are depending on. Now, in the list of literature, I didn't end it for this day, but I add on the kind of online version. I put one of the papers when the colleague of mine went through analyzing all the noises which goes into optimization of the EIT magnetometer performance. So if you ever need to do some sort of optimization of your experiment, you can look at this paper and see kind of how it is done for some system, and you can kind of mimic the process for your own. But let's say you characterize your system, you optimize the performance. Now, if you want to actually know how sensitive your system is, the part of this optimization will be figuring out what noises you have. Because you can have a strong response, but if it else enhances your noises, it really not going to buy you much. So we start today talking about the noises. And the first part might be very, very experimental, super nerdy. So if you are a very, very high-level theorist, please try to survive. You know, our experimentalist guys need to deal with this every day. So when we start measuring, of course, ideally, we would have no uncertainties in our measurements. We put something in, and we know exactly what's coming out. That's not quite the case. So let's start from the very fundamental measurements. As in many of the examples I gave you, we were looking at spins and saying, OK, how we can measure the direction of the spin or precession of the spin to get something. So in classical thing, if we're thinking about spins as a magnet, in principle, we can design an experiment in which we know exactly where the magnet is pointing out. Of course, spins are quantum beasts, and that means that there will be some uncertainty in this direction anyway. And this is one of the big things about quantum in a classical realm, is that there always will be uncertainty. So very naively, if I'm trying to measure, let's say, precession of the magnetic field, I will have, so this is, I will start with the fundamental noises. If I'm trying to measure spin, I will have a projection noise. And this is kind of, no matter how I do in my experiment, I will not be able to avoid it. So for the spins. Because what it basically tells you, in uncertainty principle, if I want to know the frequency of the precession of the spins, Larmor frequency, the best I can do with the time of observation is to have it about 1. So the longer I'm measuring, the better I will know it. But with the given time of observation, that's where I'm going to be. So if, of course, we connect our precession frequency to the uncertainty in our magnetic field we are trying to measure, you know, how little magnetic field we can measure. And let's say we're trying to do it with n atoms, so n independent atoms. If all the atoms are doing their own thing, they don't know anything about each other, it's basically like running the same measurements on one atom for n time. And then, of course, the enhancement we're going to get because of that will be square root of n, right, because of the distribution. So what we have here now is square root of n times the minimum magnetic field we want to measure, times the gamma factor to transfer to frequency, times the observation time should be in the order of 1. Now, that would be the case if our observation time is fairly short. So we can just, or our spins are incredibly stable. So that means we started the precession and they just go in for as long as we're measuring them. Unfortunately, in reality, that's not the case, because the spins are going to decay here, so you'll need to go back and remeasure this. So instead of this time, we really will have to include that we have the several independent measurements which last for, well, the coherent lifetime. And then how many of those we're going to have is something like this. Okay? So what it gives us, that for very, very fundamental limit, when everything is absolutely perfect except, we are dealing with the quantum mechanics, the minimum magnetic field we will be able to measure is basically proportional to, again, proportionality coefficient, square root of the number of atoms we have, the decoherence time of said atoms, and the observation time. Okay? So that's the best we can do. The good thing, of course, is that if you have fairly large number of atoms and fairly long coherence lifetime, this is actually a very, very good limit. On many of the systems, that will go way below something you can detect. So this is a good thing. So the second fundamental limit, so here again, we're only talking about atoms. Now, how we interacting with atoms? We have photons. And therefore, we also will have to take into account that photons are quantum object, as Raul indicated this morning. So the second fundamental noise, which we won't be able to avoid if we are doing optical measurements, is what we call the shot noise for photons. It's basically the analog experiment for the atoms. So if photons have no idea about themselves, and we are trying to measure, let's say, the flux of photons, how many of them we will going to get, well, what happens? If photons are kind of independent, we can calculate the average flux. So if you look at the flux of photon as, at a given amount of time, so we know where the average flux is going to be. That would give us the classical kind of intensity. How many photons per second going to do. But just like if you said, you have a stream of people passing by, and it's not going to be exactly the same amount of people crossing the line, you will have essentially the normal distribution of how many photons you have all the time. So you will have average number, and you have some widths. Again, the kind of a good news is that this widths will be proportional to the average number of photons. Okay? And therefore, if your measurement is optical measurements and based on measuring the flux of photons, you expect that the uncertainty, let's say some sort of a phase we're going to see, the uncertainty will be proportional to the square root of the average number of photons we have. I'm very sketchy here because we're going to talk about this a little later. Okay, so this is you cannot beat. Well, you can. We'll talk about how you can beat it. But if you're doing the classical kind of super wonderful laser, super wonderful atoms, that's what's going to limit your measurements. Okay. I wish the life was so nice if that was the only problems we're going to have. Now, of course, now let's see how many experimentalists we have here. Okay, so that would be our time of grievances. Okay, so let's think about what other noises we're going to have in the experiments. Okay, any suggestions? Say it again. Electronic noise, yes. So one of the things is that whatever you're measuring, you may have your photodetector, which will have some dark noise, so there will be some counts of electrons which don't correspond to the photons. You have amplifiers, which will just throw some electrons in just for fun, which again, not going to correspond to your measurements. So electronic noise is very real, and unfortunately, in many cases, the only solution is more expensive electronics, which is annoying. Okay, more noises. Say it again. Yeah, so I will call it environmental noise because it can be temperature, environmental. So the temperature, it's a big one. For example, the magnetic field in the room If you, most of the, for example, optical tables, they're actually magnetic. So if something changes or you accidentally leave the screwdriver too close, that may screw things up. Again, usually the only solution is try to do things quicker, right? Because luckily the temperature doesn't change that much. Or of course you invest in the stabilization. So, okay, what else? What? Amplitude noise of the laser, right? Okay, so and this actually it was next one on my list because it's almost fundamental, because if you work with the lasers, the perfect lasers do not exist. So, and this one will be the laser. It's called sometimes relative intensity noise, or sorry, residual intensity noise, or RIN. So if you look at the characteristic of the lasers, you will often see that. So that means that if you look at the laser, your intensity is always kind of flickering. Nothing you can do with that. So if you're trying to measure your intensity, and this is kind of your light goes to the photodetector, you don't know if your signal changing because your laser intensity is changing or because you're actually changing it, okay? We'll show there is a strategy. Now the good things, if we start moving here, so this is, okay, I'll write it down here. These are a category of the technical noises. And we sometimes can take care of them in the experiment. We'll talk in a second about how we can, for example, fight this one. Okay, anything else? Phase noise, yes, that's another one. So for example, if I'm talking about phase noise of the laser, sometimes it's very critical for some of the two-photon processes. Especially if you manage to lock the two lasers together, it might be less dramatic, right? So for example, if you have EIT, which I was talking, or like any three-level system. So if you use two different lasers here, so this is laser 1, and this is laser 2, then your dark state lifetime will be basically limited by how long these two lasers are going to keep their relative phase. Because as soon as they change their phase, remember in the dark state, we had the term something like omega 1 minus omega 2, B, something like this. And you can see that it's phase dependent. So if the phase of the laser changes, you don't have dark state anymore. So that's why for many of the experiments, people are trying to phase lock their lasers if it's two independent lasers, or use a single laser and somehow break it into different frequency with the phase modulation and so on. But even if you do that, you actually may run into problems with the phase noise because, let's say, your two-photon resonance doesn't depend on it, but if you're, let's say you're working somewhere over here and your laser has the phase noise, which is kind of the same as the frequency noise, that can be transferred into the amplitude noise at the end, because if your frequency of the laser changes a little bit, you're going to basically move around in your resonance, and that is not a good thing. And that's actually this particular process has its kind of own name, which is the frequency to amplitude conversion. So that's why if you have an option to choose where to park your laser, you may want to park it not like at the minimum slope of your one photon resonance, because that will help you to reduce this effect. Okay? Anything else? Any other pains you experienced with your experiments? Yeah, vibrations. That's a nice one. So mechanical. And again, what can you do here? Well, first of all, try to avoid them. And second, the next kind of popular approach is to try to put, like if you have, let's say, chopper, for example, which is moving you try to put it separately so it's not touching your optical table. It's amazing how much vibration is transferred everywhere on the table. You would think it's a small thing, but it's powerful. And also, of course, if you can have a floating optical table, you want to run it because that will help you to avoid vibrations to begin with. Okay, let me see. Do I hit everything? Oh, so the one more, and it's a little bit more subtle, and it's kind of related to the laser noise. So for example, in EIT, we can say, okay, if our probe laser is noisy, has some intensity noise, that's bad because this is what we're detecting. But sometimes you have to be careful. For example, if your pump laser or control laser is noisy, you can say, well, I don't detect this. But what can happen is that sometimes, we're number 6, the amplitude noise can couple in through light shifts. Okay? So even though, for example, for the 2-photon experiment, you don't detect your noisy coupling laser, because position of your resonance is affected by the intensity of this laser. If it's changing, your laser is changing. It can also give rise to the systematic effects. If intensity of your laser is slowly drifting with temperature, let's say, that's what you're going to see at the end. So that's why anybody who's trying to make a sensors, we absolutely hate light shifts. And we're really working hard trying to minimize the effect or making the measurements in a way where we kind of cancel out the light shifts at the final results. Okay? All right. So any more last call for noises? Yes. Polarization noise. Yes, that's another one. 7. Especially if your experiment is sensitive to the polarization, there are many ways where you have to be careful with that. If you have any polarizing elements, for example, after optical fiber, do I have the victims who had to align the polarization before? And there is really no good way of doing that. So we have one fiber which we managed to align really, really well, and now anybody prohibited to touch it, because we know we're not going to reproduce it any less. Like it's going to die with the laser, but it's untouchable part of our experimental setup. Okay, so what strategies we can set to have some of the technical issues? And I just want to show them out because they will be important even for the quantum enhancement, which I'm going to talk next. So as I said, the problem is that if you have a kind of single beam measurements, so you send your light. Let's say you have, I will pretend that it's kind of quantum, or that will correspond just to fluctuations, some sort of a noise we have over here. Then when we have, let's say, average level of intensity, then I'm going to separate just for future the short noise fluctuations. Again, they're kind of intrinsic in on the laser field. This cannot be reduced even if laser is really, really good. And then, of course, we have some sort of a technical noises. For example, the laser intensity noise is the first one to look at. So if we have this intensity, and it goes into the photodetector, okay, then what comes out is the photo current. That's ultimately what we're going to measure, which basically reflects that. So its fluctuating current will be the average value plus some of the current fluctuations corresponding to the short noise plus some of the current fluctuation corresponding to the technical noises. Okay? And as you know, many of you point out, if we just measure this, you cannot say which one is which. And of course, if you have a signal, let's say we will produce a really small change in our average current. And if it's smaller than noises, well, bad luck. So that's why in many of the experiments, you try to design your measurement scheme such you can reference what you're measuring with respect to its laser. So, for example, if you want to measure small changes in intensity, you can use the intensity reference. Okay? So instead of just, let's say this is the sample you want to put in. So instead of just sending all your beam through the sample, you're going to divide it into two, where one of the beams goes through the sample, one doesn't. And then you have two detectors as identical as possible. And then you're going to look at the difference between them. Okay? So you will be looking at the differential noise in this system. And then, of course, if you forgive me, I'm not going to just repeat this for each of the photodiodes. You can see that this one is basically will be our signal, because this will have the information about whatever target I want to measure. This is our target. Since the second beam didn't travel through this, it will be our reference. Okay? So then, of course, if we're looking at the differential signal, so delta I, if we subtract the averages, that will be the signal we want to know, right? So we will have average in the signal channel minus average in the reference channel. That's our useful signal. For example, it will tell us which small percentage of our signal field was absorbed. Now, the next thing, of course, each of those beams will come with the shot noise. And the beauty of or the curse of the photodetector is that when you take a laser beam and you split it into two, the shot noise on each of the new fields will be completely independent. So if you have two independent shot noise sources or noise sources, they're going to add up. So even though we're subtracting the signals, you're basically going to have the shot noise from the signal, shot noise from the signal channel plus the short noise from the reference channel. So using this scheme will not help you automatically to get rid of that. However, the difference of technical noises from the shot noise is that if you have, let's say, amplitude uncertainty or amplitude fluctuations on your laser field, when you split it, it's going to have exactly the same uncertainty fluctuations in both channels. So you are going to subtract the technical noises. And this is signal. This is reference. And this is basically exactly why we use this balance scheme. Because even if your laser is not perfect, and let's admit that nobody's perfect, if you manage to balance your signal really well, you are able to get rid of the technical noises. So that's why, for example, for many of the measurements, you can think that it's really challenging to detect what is your shot noise level is. Not necessarily, because there are ways you can run your experiment and get rid of any of the technical noises in your lasers and only look at the shot noise limit. Okay? Now, a couple notices. So as I said, that's going to kind of help us with some of the technical noises. So this one is particularly the one we want to get rid of. It's probably not going to help with the others. In terms of electronic noise, the practical advice, if you want to realize the scheme like this, so typically if you're looking for the small signals, you will need to amplify it at the end. It's actually critically important that you subtract your signals first and then amplify it, because otherwise, if you amplify each of the signals independently, you're going to add the independent noises, independent electronic noise on each of them. Then you're going to subtract them and be upset why you have so much noise. At least if you subtract them first and then invest in a low noise amplifier, you're actually much better off this way. Okay? And another, again, technical reasons is that make sure your detectors as close in their performance as possible, so the bandwidths are the same, so when you start measuring different timing of the signals, you don't run into the problem that one detector is slower than the other, and suddenly you see some really weird stuff in your spectrum analyzer. Okay, so again, this is kind of for intensity measurements, and what can we do with polarizations? So let me just solve it right here. So for example, if in our measurements, instead of looking at the changes in polarization, we want, instead of looking at the changes in the amplitude of electromagnetic field, we want to look at the change of polarization. The kind of standard way of doing this is taking a polarized beam splitter, right? And if then polarization changed by the small angle delta phi, that's our signal change. The nice thing is that if we direct the main polarization at 45 degrees, then of course the intensity on one output is going to be your original intensity divided by half, 1 minus cosine 2 delta. And again, here we'll have the short noise. Let me write it down. Short noise plus technical noise. And if you look at the second channel, we will have something very similar, I0 over 2. But this time it will be 1 plus cosine of 2. OK, that's going to be, 2 delta phi. I forgot phi. 2 delta phi. OK, so again, this is our signal. And just right before, we will have a short noise, and we will have a technical noise. OK. Now, if we assume that the rotation is so small that intensities are basically equal, we're looking at a very small variation between them, then we can figure out the small rotation by the difference of the two polarization. Let's say I2 minus I1. And if you subtract them, you will see that this is equal to I naught cosine 2 delta phi. As usual, you will have basically a double short noise because these two fields separate. And you may be able to get rid of some of the technical noises. So again, if you have the amplitude noise on your fields, it's going to cancel out because it will give you the same background. Unfortunately, if you have a polarization noise, that's not going to cancel out because it's basically going to mimic your signals again. So that you will need to employ some other strategy or try to stabilize your polarization for that. OK? All right, so this is kind of more nitty-gritty of how we run experiments. Any questions on that part? All right. So let's say that you are brilliant experimentalists. You figure out all this technical stuff. Your lab is in perfectly stable condition, and temperature is so stable you don't need to worry about that. Everything is perfect. That means that in this type of experiment, you're basically looking at your two fundamental noises as your enemies. And basically, when people talk about quantum enhancement of the experiments, in many, many cases, they are really trying to fight these two problems. So one is that if you're starting to measure spins, the spins are independent, and therefore you will have this natural noise in the spins. And the second one, you're using the photons. If it's an ideal laser field, it's a coherent field, the photons are independent, and that creates some uncertainty as well. Okay? There is a lot of work on how you can create the collective spins, collective spin states, it's spin squeeze state and some other exotic spin states, where you can, instead of having this many independent spin, essentially create like one super spin where all the spin behave exactly the same way. So you have this giant one vector which you can process. You can see here that instead of scaling the square root of n, that will, in some ideal world, will give you 1 over n performance, which not really the case, but you can dream. I'm not expert in that because spin squeezing, again, it is possible in the hot vapor. It's really, really hard. That's where really the cold atoms shine. So I'm sure there are people in this room or in the community which can tell you much better about spin squeezing than I do, so I won't be telling about this. Instead, I will concentrate on the photonic part. Because that one, as I said, it's pretty universal if you're using the optical measurements. Okay. Now, quick question. How many people here have seen the quantization of electromagnetic field? So pretty much majority. All right. So let me then, that's great, wonderful. So let me very quickly go through kind of pictorial things, and I will try to add some of the equations where they need to. Okay. All right. So this is, again, this is kind of original illustration of Y signal to noise measure. I was supposed to put them earlier when we just started this discussion. So let's just illustrate that when we're looking at sensitivity, there is a signal to noise. It's kind of how many resonances do you see on this curve? Well, if you look really carefully, there's actually 3. There is one little in the middle, and that shows you that if your signal to noise is less than 1, it's really hard to see it, but it is there. Okay, now I need to get rid of this thing somehow. Right? So it's still not great, but you can see it, okay? So this is, again, this is supposed to illustrate that if you do your differential scheme as you want, you can definitely help, but you cannot avoid the noise completely. Okay. So, and for those of you who might not have a quantization, so that will be a very short crash course on what quantum mechanics does with light. So if you go to introductory physics classes, they will tell you that electromagnetic field is this sinusoidal wave, which is a lie, but it's a good one, so you can kind of use it for many cases. Now, I can actually write down any wave as the combination of two kind of orthogonal quadratures. One is with sine and one with cosine. So here I'm calling them x1 and x2. And it will describe exactly how electric field behaves in a space. Now, if you know how to quantize electromagnetic field, then they will teach you that essentially the form of the wave stays basically the same. But now we will have to add this creation and annihilation operators A and A dagger. And what it tells, I actually really love this image because it kind of explains all this wave-particle duality to you, because you definitely have waves. That's how all the propagation behaves. But the A and A dagger tells you that you only can create photons by the given amount of energy. So that's your particle part. And then, of course, if we want to write it down in the same kind of way, we can write down is in terms of the quadratures. And you can see that quadratures are going to be combinations of A and A daggers together. Now, I don't think I have it on the slides. OK, so let me then just write down that quadrature x1 is going to be A plus A dagger divided by, I think, 2. And the quadrature x2 is going to be A minus A dagger divided by 2i. So that's what we're going to get. And you can see, yes, and you can see that now, because A and A dagger do not commute, that means that 2 quadratures are not commute. So your electric field, if you're trying to measure electric field of any optical field, suddenly you cannot get a precise value because it consists of 2 non-commutable operators together. So if you measure one precisely, the other one will give you no information. And of course, you can look at the Heisenberg uncertainty principle and figure out that their joint uncertainties should obey the uncertainty principle. Okay? So again, I'm probably not going to go too much into specifics. If you know it, you know it. If you don't know it, I'm not going to teach you in 5 minutes. But if we take a laser and kind of take a perfect laser, so no technical noises whatsoever, the laser output is going to be a coherent state. Now, of course, we talk about word coherent a lot, but when we talk about quantum optics specifically, coherent state has something very specific, and it tells you that basically coherent state is determined by its alpha, it's a definition, and the specific coherent strength, it's an eigenvalue of the annihilation operator. So essentially, and in this case, we can measure that alpha is going to be the kind of average value of the field. And we can see that the average value of one quadrature is going to be basically real part of alpha, or the average alpha times cosine, some phase. What I was using, OK, I don't remember what I was using for phase. Pi? What I was using for phase. I don't remember what I was using. Sorry. Chi. OK. So phase chi. And then, of course, the other quadrature is going to be the imaginary part of alpha. Again, the amplitude times sine chi. And if we look at the classical description for electromagnetic field on top, that's exactly what average value of the quadratures are going to be in the coherent state. So that's actually why we don't have to yell about quantum properties of laser light all the time. Is basically because it's actually very close to the classical description of electromagnetic field. Just for fun, for example, this is experimental data when people were measuring the electric field of the coherent state with a different amount of photons in them. One of the great properties of the coherent state is that no matter how many photons you have, the uncertainty of each of the quadratures is going to be exactly the same. It is going to be 1/2. So that means is that it doesn't matter how many photons, how much energy you put in the state, your uncertainty is always going to be the same. And this is the illustration of it. So you can see if your average number of photons is really small, so if it's 4, then it's clearly a very noisy electromagnetic field. So every time you measure it, you have a lot of uncertainty in both its phase and its amplitude. However, if you have 25 photons, it's definitely getting a little more noisy, but it's better. If you have 1,000 photons, which is still a tiny, tiny amount of energy, it's nowhere near the amount of light you have in a normal laser beam, you already barely see any uncertainty. And you can see that if you, let's say you have a 1 milliwatt of laser light, that's, if my wild estimate is correct, it's about 10 to the 16 photons per second. So the amount of uncertainty you're going to get, again, square root of this photon, 10 to the minus 8. So that means that fundamental noise on your laser is going to be at the level 10 to the minus 8. Very few experiments are that sensitive. There are some, for example, when people trying to measure gravitational wave detection in LIGO, they have to be super sensitive. But that's why they're already on a short noise limit, and they need to fight with that. So they're really trying to beat it. Okay? So again, if you are not doing this type of experiments, you can say, OK, I don't have to worry about quantum mechanics. My lasers are good, classical description, and it all works. Where the quantum noise really becomes critical is actually the differential schemes we were discussing. Because there, if you balance everything really well, your signal ends up being 0, but the noise in of the field is still going to be proportional to the number of photons you're sending in. So that means that you basically will be somewhat limited by how small a signal you're going to measure it by these fluctuations in your field. Okay? Now, what can we do with that? So this is kind of a classic for quantum optics description of the quantum field, where we kind of display the two quadratures, and the thin solid line here shows you basically the alpha. This is the average amplitude of your electric field. I like to think about this as kind of trying to visualize the electric field in space in some moment of time. If I repeat these measurements, because of the uncertainty, I'm kind of not quite sure where my vector end up. So we have some noise ball. If you want a more fancy description, it's actually a visualization of the Wigner function, if you know what Wigner function is. But, so this is what this image will tell me kind of visually, is that for the coherent state, I have an average value, and also I have this noise ball, which is equal, it's no matter what I'm doing. Now, in the experiments, I usually have to choose which quadrature I measure. If you just send the laser beam kind of on your photodetector, typically you measure quadrature x1. This is intensity quadrature. But as we see very soon, you can arrange your measurements such that you choose which quadrature you do. So that's corresponding to kind of rotation of your stick on the ball, and you choose which vertical projection you are measuring. For coherent state, it actually doesn't matter. That's why we don't have to worry about it for the normal laser field. Now, but let's say you know what kind of measurements you want to do. Suppose that you're doing intensity measurements, just like here. So on the output, you really want to know what amplitude difference your signal is. So that means is that you would love to reduce the uncertainty in your intensity quadrature. You're losing information about phase quadrature in this case, the second one, but you don't measure it, so you don't care about it. So what you can do then is to create a special state of optical field in which you take basically this perfect round ball and you kind of squeeze it. You cannot get rid of the uncertainty principle, but you can make one quadrature fluctuations less at the extent of the other quadrature. That's exactly what squeeze states are. And this one, for example, kind of represents the noisy squeeze state, which is the phase squeeze state. You can see that if you look at the phase, that's where it crosses the zero line. That's how you're going to measure phase. It's much better at expense of much larger amplitude noise when you're trying to measure this. But again, if you want to measure phase, maybe you don't care about this. And this is basically what the main essence of how the squeeze light is used to enhance the optical measurements is you need to design the quantum probe with the right properties, and you need to design your measurements to measure the right quadrature. And in this case, you can have your fluctuations less than the shot noise. Again, this is kind of the basic. So that's why when we're talking about fundamental noises, shot noise is not really a fundamental noise in the sense that you cannot go below that. You can, but not if you have your coherent light, which is kind of classical version of it. Okay, just again, just to say for many of the measurements, you can have squeezed light, but you can also have squeezed vacuum. And again, for those of you, if you haven't talked about quantum optics enough, electromagnetic vacuum is a fascinating thing. You used to think about vacuum as like nothing, and it's so far from that. It's like if you imagine that the concept of electromagnetic vacuum disappears, like I don't think we can even survive, right? Because the lifetime of all excited states is given by this vacuum. So just think about it. If there is no vacuum fluctuations, there will be no spontaneous emission, so there's no light in this room, no light anywhere. That would be a very bleak, bleak space. Vacuum of electromagnetic field, of course, it's basically the ground state of your oscillator. If you remember the quantum oscillators, they never stop. So there is always something going on. And that means that even if you don't have any photons on your electromagnetic field, they're still wiggling a little. And they're still disturbing everything around them. Now imagine this kind of wiggling nothing, and then you're going to squeeze it. So what it means is that if you design your measurements where you're sensitive to the fluctuations of this vacuum, and we'll talk in a second how you do that, now you can make sure that the two quadratures of this vacuum field, because remember, we are not specifying that you need to have photons in it, they will be different. So that's called squeezed vacuum. Now, what it really means is that, again, if you make the measurements, that's more of the practical thing, if you make the measurements and you somehow change which quadrature you're measuring, if you're using the coherent field, as we discussed, you're going to have the same noise everywhere. And So that makes the experiment easy because you don't have to worry about the phase anymore. However, if let's say instead of normal vacuum you use a squeezed vacuum, in this case, depending on the phase in which quadrature of this vacuum you're capturing, you can go below the short noise limit, but by very specific quadrature. In this case, if you characterize kind of the squeezing of your ball by the squeezing parameter minus 2R, you can reduce the noise by this factor. So you will be doing better than short noise. Again, the price you're going to pay is that in this experiment, you will have to keep track of which quadrature you are sensitive to, because as you can see, if you happen to be on the wrong quadrature, you're actually dealing with more noise than you want, than the coherent state. And what, again, the kind of some of the brutal reality of the squeezed field. Technically, the amount of noise you enhance below and above the short noise limit are supposed to be the same for the perfect squeeze state. We will talk a little bit later is that squeeze states are very sensitive to losses. And the squeezed part, the squeezed quadrature is kind of more sensitive to losses than the anti-squeezed quadrature. So that means that for majority of the practical squeezed field, you have way more anti-squeezed noise than you have squeezed noise. So you really have to be very careful about this. And this is kind of a little bit of a sour point for the quantum enhancement with squeezing, is that it adds experimental complexity, and sometimes it's hard to justify this added complexity to the improvement of the sensor performance. Okay, all right. So now let's go back to the board. Let me see, where is my notes? Okay, so okay, so now how you can actually measure this? Because okay, I can draw the fancy diagram which shows you the noise ball changing, but how we can do that? So because we need to measure the, to choose which quadrature we detect, we need some sort of a reference for the phase. So that's why in our system, we will need to introduce a local oscillator, which will be our reference, and it also will allow us to amplify our weak vacuum field. So just for fun, let me add here that if we write, see, where is it? So if we want to measure any quadrature, so this is again this is intensity quadrature. And this is phase quadrature. Okay, so if I want to do something else, so my quadrature in some other angle, and then that's going to be theta, let's say chi. I'll explain why I call chi in a second. And it's going to be defined as 1/2 a e to the minus I chi plus a dagger e to the I chi. Okay, so that's a generalized definition of a quadrature. Okay, so how are we going to do the detection then? So let's say we have our signal field. So we have our, let's say, squeezed vacuum. Or in general, any quantum field we want to analyze. Okay? So now we're going to mix it on a beam splitter with the local oscillator. So this arrangement, and we're going to detect, of course, the outputs from this mixing. So this arrangement is called the homodyne detection. Homodyne, it will be if the local oscillator and your signal whatever you want to work with is the same frequency. If they happen to be of a different frequency, that will be heterodyne detection. There is actually nothing intrinsically fancy quantum in this system. This system was invented for the radio, because that's how the signals are connected in your radio. The radio station sends the weak signals, and then in your radio detector, the car probably, you have actually the local oscillator, and when you tune, or now I think you push the buttons, that actually changes the frequency. So every time you match some of the frequencies from like weak signals from outside, you have the amplification here. So for some of the experiments, you actually might use this technique for a very classical field just to amplify what you get out. But we also happen to use it for the quantum fields. So in this case, I'm going to switch a little bit to the transformation for the annihilation operators, just because it's make calculation a little bit easier. So if we have our signal, and we have our local oscillator coming to the beam splitter, we can go and see is that on one of the outputs, let's say one of the outputs, like I will call it channel C, we're going to have 1 over square root of 2 a signal plus I a local oscillator. Okay. So I'm giving this without derivation, but it's if you look at how the how the beam splitter transforms the two optical fields, you're going to get that. And of course, on the other channel, we will have something very similar, except we'll have a different phase over here. So a signal minus I, right? No, we will have a I signal plus a local oscillator. So kind of extra phase migrate over here. Okay. Now, this is basically how we're going to do that. Now we need to know what is going to be if we're going to detect the photocurrent on two of those and subtract. So it's going to be the same differential scheme which we discussed before. Now I will need to calculate how many photons arrive here and how many photons arrived on this detector. Okay, well, we'll do a little bit of algebra then. Actually, let's do this. So you have this transformation. And of course, the average number of photons, as you know from your quantum class, it's just this. Okay? Let's do it in parallel and then compare, because I'm pretty sure I will do some typos there. So use this expression for AC and AD, well, for this one, AC. Let's all of us try to independently get the final expressions of what is the number of photons is going to be there. I think it will be a little more fun to look at that. Okay, so I will be just writing quietly. You do it yourself, and then you compare and tell me what I did wrong. How you guys are doing? Did you get the same thing? Okay, so what you can see is that because now the two outputs from the beam splitters, they will have a relative phase between the two fields. That means that if we're starting to look at kind of amplitudes of the fields or the number of photons, whatever you want to look at, some of the terms are going to be exactly the same, but some of them will have a different phase. And that's what we're going to exploit. Again, it will be the same for classical measurements or for quantum measurements. Basically, if we're looking at the difference in the number of photons we're detecting, we basically will be looking only on the doubling the cross terms, and it's going to be I signal A dagger times the local oscillator minus AS times local oscillator dagger. Okay? So this is exactly accurate result. So in this case, we made no assumption about local oscillator be stronger or weaker. So in principle, it will be true even if you send two completely quantum fields and want to manipulate them this way. However, for this particular measurements, we will assume that our local oscillator by the way, the name of it, again, that comes from the radio, that because you have your oscillator here, except the signal is somewhere else. We assume that the local oscillator is it's a strong coherent field. So in this case, just as we discussed before, a strong coherent field is basically a classical field. The variations are so small, we don't care about this. So we can say that the local oscillator, so the average of alpha is going to be the value, and it's going to be its amplitude times e to the phase of the local oscillator. That's what we're going to control in the future. And then basically for the local oscillator, we can present it as the average value, alpha of local oscillator, and only leave the fluctuations of the local oscillator as a quantum field. Now, I'm going to not to go through all the steps. What we will see is that when we substitute it over here, any fluctuations of the local oscillator will be multiplied by the strength of our signal. And if our signal is weak, basically, we're not going to be sensitive to it. Again, you can do it, we can do it precisely and see why it is the case. But here, I just basically going to stand because the local oscillator is a strong coherent field. We really don't care about this. So that means that I can simplify my expression for the photon number difference, which we're going to see. So it's going to be alpha. Now, the quantum field for the signal, I dagger. Now, then for the local oscillator, I'm going to replace it with this expression. So it's going to be amplitude of the local oscillator times I chi, minus here I have a local oscillator dagger, so I will need to complex conjugate. So I will have signal of the local oscillator into the minus I chi, okay? And of course, since the local oscillator amplitude is just a number, I can write it down as AS e to the minus I chi plus AS dagger e to the I chi. Okay? And this is what it reminds you of. It's almost this quadrature, but of course it's almost that, because you need an extra phase 2. So basically, if we replace chi with the chi plus phi over 2, I mean, I could probably cleverly do it in the very beginning, but then it would look really weird. Then we will basically have exactly the same thing. That will be double of our chi with this replacement. That will be our quadrature. So that's actually pretty cool, because now the output of the photons gives us exactly, and again, we assume that the average numbers are the same, so it's the fluctuations in the number of photons we're going to see here. it's proportional to the quadrature of our quantum field, but it also multiplies by the amplitude of our local oscillator. So that means suddenly I can make it theoretically as strong as possible if I use the strong local oscillator. Okay? Now, how are we going to actually measure it? Of course, in practice, okay, let me erase this. What is going on is we're taking the current. So these are our two detectors. So now we're taking these two signals. We subtract them from each other. So that will give us the photocurrent, so differential photocurrent, which is basically proportional to the fluctuations of the photon numbers. And then we're going to send it to the spectrum analyzer. So this is basically our current noise, well, current fluctuations. Again, practically, we're going to send it through some sort of amplifier. So we never measure current, we only measure voltage. So we convert it into the voltage fluctuations by, adding the resistor and amplifier. And then we send it usually to the spectrum analyzer, which measure the noise power. Right? So we don't measure the voltage, we measure the power fluctuations in our signal. Oh, we have that. And the power, of course, is proportional to the square of the photocurrent average. And that's, of course, is proportional to the square of average variation of the photon number we calculated. And because that number is proportional to the quadrature, we're basically measuring the quadrature squared of our field. And again, if we assume that this is it's measuring on the 0 level, so this is the quadrature fluctuations. Okay? So this is how we do in these experiments. So we build in this detector where we add the strong local oscillator to our quantum field. I mean, obviously, I'm thinking about squeeze noise, but it can be any quantum field you want. People have used this detection, for example, to reconstruct the single photon wave packet and so on. And then you analyze the photon difference, which in the experiment, you end up measuring the noise power of your photocurrent from your photodetector. And in this case, again, if we expect, for example, we have a coherent field, so if you have, okay, let me write it down like this. If our signal is the coherent vacuum, right? So in this case, basically, you don't do anything. So this is an empty port. You don't do anything. You could think you have anything, but it's actually not true, because in this case, your quadrature, no matter of which angle you have, would be equal to 1/4. And therefore, your current for the coherent field will be proportional. Of course, I'm skipping all the conversion factors between the quadratures and the actual current, will be proportional to the local oscillator squared times 1/4. And it will be basically proportional to the quantum oscillator intensity square. So when you measure the variance of your current, it will give you the variance of your vacuum, which will be proportional to the local oscillator. That also tells you that in the future, if you have sorry, let's see. So this is going to be, sorry, I missed that. So that's going to be the variance of your quadrature, right? So this is called variance. For some of the definitions of the uncertainty principle, we often look at just delta x, and that would be proportional to the, not the kind of the power of your laser, but for the square root of the power of the laser, and it's one of the characteristic things about squeezing. You can check if your detector is actually measuring squeezing. Okay? So that just illustrates that even if you have your field and you're trying to measure it on the differential scheme, you notice that you will have some short noise over here just because your vacuum port is not empty. It's going to add some of the fluctuations there if you want to think about it. Of course, if you use the squeezed signal, so if our signal is a squeezed field, in this case, it really matters which quadrature you are measuring, because you can measure you can adjust your phase of your local oscillator to measure the squeezed quadrature, which in our case will be e to the minus e to the 2r. R is a kind of squeezing parameter. But if you change the phase of the local oscillator by the factor of 2, by 50 degrees, pi over 2, then of course you will be at the anti-squeezed quadrature, which is e to the minus 2r. And this is actually exactly what this image represents. So this is the output of the homodyne detector, where we're changing the local oscillator phase by rotating your wave plate. And you can see that if we have a coherent vacuum, in practice it just means we're blocking whatever comes out of our vapor cell, so we send in nothing. Nothing changes when we change this phase. However, as soon as you start in the change, or if you start to send in the squeezed vacuum, you're actually going to get some variations in your noise. And of course, if we want to use it in our experiments, we want to see it on the bottom. So that means we will have to control the phase over there. And you can also kind of see how you can help yourself, because here, of course, I use the local oscillator as kind of universal reference, which just used to amplify it. But you can also imagine that I can go through exactly these calculations and say, okay, my local oscillator is the signal I'm trying to measure, right? So in this case, I'm actually trying to measure how much of an average signal I have, and whatever the fluctuations I was calculating, that will be the noise I'm going to see. And therefore, you will want to provide the squeezed vacuum on the other port of your beam splitter to potentially reduce the noise on your on your measurements. And this is exactly how it's used, for example, for LIGO or for other quantum-enhanced experiment where the squeezing is done. Okay? Make sense? Questions? I've been talking for a long time. Okay? All right. Ooh, 15 minutes. All right. So just again, a practical note. If you're looking at pretty much any paper reporting any amount of squeezing, squeezing will be reported in dBs. So if you have 1 dB of squeezing, they say, eh. If you have 3 dB of squeezing, they might start talking to you. If you have 10 dB of squeezing, like, wow. If you have more than 10, they will start questioning if it's accurate or not, because it's extremely hard to get. The best squeezing, optical squeezing I know of is 15 dB, and the guy who does it is a magician. So, well, quantum magician. So how we go between, let's say, this and dBs. So if you want to know it, so basically your squeezing in decibel is defined as 10 logarithm, so base of 10, and then you look at the ratio between your fluctuations of your squeezed field divided by the fluctuations in the coherent field with the same amount of average photons. So again, in our detector, that also means that we look at the fluctuations of the photocurrent, which corresponds to when we have the input for the squeezed field, divided by the photocurrent if we send the coherent field with the same amount of photons. So if it's vacuum, it's 0. If it's non-vacuum, it should have the same amount of this. Oh, sorry, yes, coherent. Yes, thank you. OK, now I know at least one person pays attention. Thank you. OK, so squeezing is wonderful. Squeezing can help you. So why wouldn't we put squeezing everywhere, right? That's a good idea. And that's because everything which is good is usually fragile. And squeezing is quite fragile. It's very sensitive to losses. In the next slide, I will try to explain kind of pictorially why. All right, let me erase that. So we already know this thing. But losses really make squeezing worse. Why? Because they mess up our wonderful performance. So one of the very typical way of how we count for losses in the quantum optics is if we introduce it's kind of a beam splitter. So let's say you have 10% losses when it goes through whatever happens. Well, you can imagine that basically it's like you have a beam splitter which transmit, let's say this is your input field, and then your output field is whatever transmission through your system happens of your input field. Well, of course, if it's a beam splitter, something goes somewhere, but we don't care about this. We're not going to detect it. So you can say, OK, that would work pretty well for classical description. So can I use it for the quantum description? And then, of course, let's see, I will write down that the quantum operator of out equal to transmission coefficient times the annihilation operator of the field in. Okay? Now, if you know the answer to the question I'm going to ask, find the person who doesn't and enjoy yourself. Okay? Basically, don't say it aloud immediately. So if you don't know this, what's wrong with this? Like, why it cannot be true? Talk to each other. So why, anybody who kind of knows quantum mechanics and what are the properties of A and A dagger, why this statement cannot be true, assuming that T is, if you have losses, is less than 1. OK, since we don't have tons of time, any suggestions? Say again? OK, so you know the answer. OK. But let's say you kind of offering the solution. But let's first identify the problem, OK? So what is the problem with a statement like this? Why I just cannot continue and say, OK, this is how I'm going to continue to describe my field after losses? I'm going to give you a hint. For the creation annihilation operator, we have a pretty kind of famous commutator relationship. Do you remember what it is? Yeah, so we want the A dagger A to be equal to 1. OK, so let's say this is true for the input field. Now I'm going to substitute this is here. And then for the output field, I'm going to get, I don't remember exactly, but something like this. So the more losses we introduce, the less the commutation relationship is going to be. That's a problem. And why it is the problem, again, you know this, is because we kind of ignored the vacuum port of the beam splitter. In quantum optics, vacuum is the full-time player. So we have to take into account that there is a vacuum, the coherent vacuum, entering from another port. So as a result, instead of just having our reduced field as we used to in classical description, we will have to have some of the vacuum field added in. Okay, let me make sure I don't mess up too much. Okay. So that means that if I go and write down the quadratures for this expression, we will find that it's T input quadrature transmission minus R vacuum quadrature of the other one. And by the way, you can confirm that if T squared plus R squared are equal to 1, which is the case of the non-lossy beam splitter, that's exactly will preserve the commutational relationship. So that means that if I have my field and it goes through some losses, when I'm measuring their fluctuations after this encounter, you can show that it's going to be transmission coefficient for intensity, so that's the actual transmission, when we say transmission is 10%, it's this one for intensity we're talking about. So we have transmission coefficient times whatever the original fluctuations of the field were. But now we have an intrusion of the vacuum fluctuations because of the losses. Now, if we assume that this is a coherent vacuum, if nobody was nice enough to provide some squeezed vacuum on this channel, that means that this is going to be basically 1/2. So the output is going to be T, whatever delta X we had before, plus, well, we said this is 1 minus T times 1/2. So that's what you're going to get. Now, and this is actually, it might not look too bad, but it's actually pretty bad. So let's say we have one of those amazing squeezing detectors, and it's so good, it's 10 dB. So that means if we have a 10 dB of squeezing, that means that the fluctuations of our field, let's say fresh off our squeezer, is going to be 10 times less than for the corresponding coherent field. So it's going to be 1/10 of 1/2. We're very proud of it. Now, somebody accidentally left the uncoated glass. That gives you about 10% losses in your path. So in this case, we have the T is equal to basically 9/10. Okay. Well, try to calculate by how much worse that becomes. Okay. Do you guys have the calculators around? Let's do a little bit of algebra at the end, okay? So if I started with 7 dB, sorry, with 10 dB, how much worse the squeezing is going to be after that? Freudian moment, Freudian slip. It's actually, it will be more accurate to say it's minus 10 dB. Okay? So first, we will need to do this calculation, right? Huh? Okay, sorry, you have to be a little louder. Okay. So let's start from here, right? So we will have transmission 9/10. This quadratures will be 1/20. Then here we will have reflection 10th, so this is the remaining of the losses, plus 1/2. Okay, so we have 9/10 times 20 plus 1/20. And we're going to have 19/200. Now we will need, so this is again, this is with the relatives. So then we're going to need to plug it in onto this equation. And we will find that output squeezing is minus 7.2 dB. So just adding this 10% losses already dropped our squeezing quite a lot. If you have 80, I think you lose half of your squeezing and so on. So what it means is that the squeezing enhancement is working only when your system is basically loss-free. If you have everything nicely optically not lossy, you're actually going to get maximum enhancement from the squeezing. And that's why we applying squeezing for some of the atomic systems is tough, because if we work on resonance, that's intrinsically have a lot of losses in it. And therefore, whatever advantages of squeezing we may have, we are likely going to lose them at the end. Okay? Now, with the calculations, I talked a lot about squeezed vacuum, because for many of the measurements, squeezed vacuum is exactly what we want to, again, to add to our measurement system, to any empty port which adds vacuum in it. But you can certainly have a squeezed coherent field. Well, you can look it up. It's fine. I cannot find it right now. Now, what makes the squeezed vacuum special? Remember, in the very beginning, I was talking about coherent state being a state with independent photons. The photons don't know anything about each other. If we go through the squeezing operator and calculate what is the squeezed vacuum state in terms of the photon number, you discover a couple interesting things. So first of all, squeezed vacuum actually do have a little bit of photons in them. The number of photons is proportional to your squeezing parameter, so the stronger you squeeze, the more photon you have. It's still a few, but you definitely have them. The second amazing thing you will discover is photons comes in pairs. In ideal squeeze state, your photons will come in pairs. And this may not be a huge surprise if I tell you that the squeezing operator, so the operator which describes the generation of squeezing, looks something like this. E to the, I think without I, okay, I'll double check. Basically, your squeezing parameter, A squared minus R star A dagger squared. I'll confirm in a second. There might be some sign change over here. But anyway, it looks something like this. Yes, so it's 1/2 and star over here. Okay. And you can see, so basically, if we start with the vacuum state, which has no photons, squeezing operator will be adding or removing the photons only in pairs. So that's why we will have the interesting states which has no 1 photon, no 3 photon, no 5 photons. So that will give us ideal squeeze state. Now, what losses are going to do if we're thinking of this? They're going to nip some of the photons out. So that means we start to messing up our perfect pairs, and some of the photons will go uncoupled. So we start to populate those states. And this is actually, again, is kind of famous experimental plot where people were actually measuring the photon distribution in the squeezed vacuum state. You can see the difference between the ideal and real. You can certainly see the disparity between the even and odd number of photon states, but they're definitely not as dramatic. And that's why the losses are so bad. Because as soon as you start removing even a little bit of the photons out, you break this asymmetry between the two states. And for some of the measurements, so everything I was talking about is called the quadrature squeezing, where you basically work with one field. There is, for quantum sensors specifically, there is another type of squeezing which is very popular in terms of generation and application, and it's called a two-mode squeezing. Some people call it two-squeezed vacuum, which is very confusing because you actually have two bright beams coming out of your setup. So it is a very confusing vacuum with you have many, many photons in each of the fields. But it's, again, like historically, you start with a vacuum state to do that. And in this case, instead of creating the photons in the same mode in pairs, you create them in the different modes in pairs. And again, for the intensity difference, if you look back at the differential detection, sometimes you can use one of those fields as your reference, and one is the measurements. And you really only see the quantum fluctuations in this intensity because the photons are created at the same time if you subtract your intensities. In fact, each of the fields individually typically more noisy than the coherent field. Okay? All right, so in the remaining 30 seconds, how, if I convince you that squeezing field is great, where you can get one? Well, there are multiple, basically almost every nonlinear optical process can be somehow connected to squeezing if you work hard enough. The classical squeezing, so if you just go to find something, will be parametric down conversion. And you can see that it's kind of built for squeezing because you create a one pump photon and you split it into two. So this is your pairs. This is automatically how you get them. So it's done in nonlinear crystals because for atoms, for example, it's really hard to create the chi2 nonlinearity. Atoms too symmetric for that. And the nice thing, you can create them on different wavelengths, but it's also fairly broadband, so it's why it's hard to, and not always on the right wavelengths. Another mechanism is the four-wave mixing. This is historically how the very first squeezing was absorbed. And in this case, you have two pump photons, which are converted into probe and idler. You can use it to generate quadrature squeezing. If it's degenerate process, you can generate the bright two-mode squeezing if this process. It has been done with atoms, as I showed in my talk. You can definitely do it in the crystal. Because it's chi3 nonlinearity, it usually requires more power or more nonlinearity. But on the other hand, it can be produced in a broader state range of materials. More exotic things, again, these are probably the two most classical ones. Definitely the interest in optomechanical squeezing becomes, because if you create a system where the mechanical vibration of your system are connected with a number of photons, now you can adjust your system such that, for example, behavior of single photon and the two photons is very different. So that means that the statistic of the light which goes through your system, you can kind of preferentially pass the even number of photons versus the odd number of photons. And from the practical point of view, more and more interest are spent on looking at the squeezing in fibers or the microresonators. And in this case, of course, in the microresonators, you create many different modes which are kind of connected to each other through the resonator. And that's a very effective way to produce squeeze light in the whole broadband. And it's this particular states, they're actually very interesting for quantum information, to creating photonic cluster states and stuff like this. I don't understand them. My head just cannot approach them, but it's very, very, very exciting topic. Okay? And finally, just because you spend so many hours listening to me, I wanted to point out that quantum sensors, of course, why we do them is because it's fun. I hope it's okay if I quote Feynman here. He said, the fundamental research is like sex. It has practical application, but it's not why we're doing this. However, for quantum sensors, actually people starting to find the practical applications. So I was this review was published literally a couple days ago, and I did put it in my list of literature. I can tell you that I had to jump some hoops to get the PDF, so if you want it, email me, I'll send it to you. I'm not quite comfortable putting it online. But now people are actually very seriously looking at, if you can't read, these are the real applications, people trying to apply the quantum sensors on a very broad range of how we can improve our lives to that. Honestly, I do think they're a little bit too optimistic, but I'm definitely willing to jump on this bandwagon. Okay, so this is it. Again, I want to thank you guys for being a wonderful audience. I had so much fun working with you, and I hope we'll stay in touch. Bye.